Good morning and welcome to today's session of Orkney International Science Festival. Now, if you ever want a scientific anchor to navigate you through the storms of life, well, it has to be the National Physical Laboratory. That's the place that look after the standards that are behind the billions of measurements every day that run through the social and commercial world globally. It's a whole science of measurement called metrology, and Richard Brown is the head of the section, head of metrology at the National Physical Laboratory. Richard is responsible for the accuracy of the UK's primary standards of measurement and their compatibility internationally. He's also engaged in the chemical study, in the study of chemical measurements for improving air quality. In addition, Richard's actively involved in the ongoing development of the International System of Units, which indeed is the subject of today's talk. So, Richard, good morning. Welcome to the session of the festival.
Thank you very much. Pleasure to be here.
Oh, we're delighted you're here. And just before getting underway, I should mention to our viewers, wherever you are, there's a way of asking questions directly for Richard, which we'll put to him at the end of his presentation. In fact, there's two ways. There's YouTube chat, but in addition, we've got this new way this year. It's a system called Slido. And all you need to do is, as the instructions on the screen say, scan this QR code with your phone. And if you don't have your phone with you, well, you can visit the Slido website, an easy address, slido.com, and simply put in this code 3435541. And that's all the numbers from me. And indeed, I can now sit back and hand over to Richard down there at the NPL and ask you, Richard, to tell us more about those fundamental standards.
Lovely. Thank you very much, Howie. Thank you for the kind introduction. So yes, this talk is called The Measure of All Things. And as Howie said, I'm Richard Brown. I'm the Head of Metrology at the National Physical Laboratory down in Teddington in southwest London. And I'll explain a little bit more about NPL and metrology as the talk goes on. So if we could have the next slide, please. What I want to address today then is 5 points. So why accurate measurement matters to us, how our measurements are expressed, where our current measurement system came from, and how we achieved international agreement on those units, and also how they've evolved over time. And importantly, how our measurement system has changed recently. So next slide, please. I will start just by saying a little bit about where I work, the National Physical Laboratory. So NPL is the UK's National Metrology Institute, metrology being the science of measurement. Now, we've been going since 1900, and since then we've maintained the nation's primary measurement standards and thereby the units which underpin them, which will form the basis of this talk. And these unit standards, these primary measurement standards, underpin the infrastructure of measurement throughout the UK and by comparison internationally throughout the world too, and they ensure the consistency of all the measurements we encounter in life. Now, NPL is about 650 scientists, little more than that, largely based in Teddington in southwest London, but we also have sites around the UK in Huddersfield, Cambridge, Guildford and Glasgow. And we're a government lab. We're owned by the Department for Business, Energy and Industrial Strategy, who run us as a public corporation. So that's enough about NPL. On with the rest of the talk. So if we could have the next slide, please. What I want to start by saying is that I think you'll realize that measurement is ubiquitous. It's absolutely everywhere in life, from the GPS on our mobile phones to healthcare, to complex instruments and machines like cars and planes, to more mundane weights and measures. It's everywhere and it makes everything function. But it often goes unnoticed in our daily life. And the thesis that I want to put to you in this talk is the reason it goes unnoticed is because the measurement system that we have underpinning those measurements works so well. So next slide, please. And the reason for that is because it's measurement that makes science scientific. Not mathematics necessarily. Maths provides a nice language for describing measurements, but it's measurement that makes science scientific. And in fact, next slide, please. If on that vein, what I want to start by introducing is the language of measurement that we use when we express measurement results. So this is a very simple example. We have a table, we want to measure its length, and we say the length of the table is equal to 2 meters. And we have 3 parts of that statement. We have the thing being measured, a number, and a unit. Now we have agreement on the thing being measured, the length of the table, because we understand words and we understand vocabulary. We have agreement on the number 2 because there's general agreement on mathematics. And nowadays, we have agreement on the meaning of meter because we agree on the units that are used in metrology. But that wasn't always the case. And the rest of this talk will be addressing how that evolution has occurred over time. So next slide, please. It's worth then digging in a bit more detail into length standards and in particularly early unit standards. So if we consider length, the early unit standards were all associated with the body, and the very famous one is the cubit from the tip of the fingers to the elbow. And this, of course, was a very convenient standard because everyone had access to their own cubit. Everyone could measure it using their own body. So it's convenient, but as a length standard, it wasn't comparable because everyone's body was of a different size. Now, the ancient Egyptians solved this problem because they enshrined that cubit distance in the body of a single individual. That individual was the pharaoh. And so all of a sudden, we had a length standard which was comparable because it was embodied in one human, but it was no longer convenient because the pharaoh had to be present if you wanted to make a length measurement. But the ancient Egyptians solved this problem as well. So what they did was they enshrined that length of the pharaoh's cubit in a cubit bar, as you see in the top right there. So all of a sudden we had an artifactual standard that was convenient and it was comparable. We could take it to where we wanted to make measurements, but it wasn't universal. And what do I mean by not being universal? Well, not everyone agreed on that as a length standard. And indeed, we see this problem persisting for hundreds of years after that, all the way through to the Middle Ages. This in the bottom right, you see an image from a town wall in southern Italy, where the weights and measures are built into the wall, so you can check that the lengths and the volumes you're buying of your products in the market are indeed what they should be. And that's all great, but the problem is that those standards built into that wall were very different from the standards built into the wall of the neighbouring village. So next slide, please. And this was embodied by a really good example of this lack of comparability, which can be found in the banqueting house in London. So if you ever go to the banqueting house in London, the banqueting hall has got an amazing ceiling, which you can see in the picture there, painted by Rubens in the 1630s. And when Charles I commissioned this ceiling from Rubens, Rubens painted the ceiling without actually ever visiting London. And when the canvases were delivered to London, to the banqueting hall, and they were unfurled and held up to the spaces that were left for them in the ceiling, it was realized with horror that they didn't fit. And the reasons that they didn't fit was because the length of a yard in London was different to the length of a yard in Belgium, where Rubens was painting those canvases. So it was very clear for those reasons and others that international agreement on units was needed. So next slide, please. But we had to wait another 150 years at least until we saw the start of this process. So the reason that we are where we are now is largely because of the French Revolution. And at the point of the French Revolution, there were hundreds of thousands of different units in use in France. And often the rich and powerful could use those to cheat those who weren't as rich and powerful. So That was actually one of the drivers of the French Revolution. And after the French Revolution, these old units of measurement associated with the king and the old regime were replaced with new units. Now, initially, the meter was defined as a 10 millionth of a quarter of the Earth's circumference. But that turned out to be quite a difficult definition to continually realize. And so soon it was replaced by a physical artifact, a meter bar, the meter of the archives in 1799, and the kilogram, which had been based on the mass of water, having the volume of 1 litre, was replaced again by a physical artifact, a kilogram of the archives. Now, both of these were placed in the custody of the French Academy of Sciences. But it wasn't long after this, another 10 years or so, that due to the unpopularity of this new metric system, France had reverted to using old units that were similar to those in the old system. And part of the reason that the metric system became unpopular was an example you can see on the right-hand side there. At one stage, even a decimal system for time was introduced. And certainly for 2 years at the end of the 1700s, the French government used decimal time and this decimal clock. And this proved to be a very unpopular change, which you will note has not persisted to the current day. So whilst France had reverted a little bit to using old standards, 25 years later, 1837, the metric system was actually readopted by France. This was not least because it was in growing use elsewhere around the world, particularly as we will see in scientific communities. So next slide, please. What happened was because more countries were adopting this system, there was a danger of a lack of comparability emerging. And so prompted by the need to unify geodesic measurement, so measurement associated with map making, 17 governments signed something called the Meter Convention in 1875. And this was a diplomatic treaty that exists to this day. And it established a permanent structure for these member states to act in common accord on all matters related to units of measurement. And as we will see initially, it just covered mass and length, but grew to encompass all of the metric system, which we now know as the International System of Units. So next slide, please. In 1875, then the Meter Convention was signed. It took another 14 years for the size of the meter and the kilogram to be agreed, and that's because they had to be forged as meter bars and kilogram artifacts. So that took a bit of time for preparation. But by the time the meter and the kilogram were prepared, it was also realized it would be a good idea to agree on the exact size of a second. So 1889, the meter, kilogram, and the second all underwent international agreement. And if we have the next slide, please, we can see that subsequently in 1954, the ampere, the Kelvin, and the candela for electric current, thermodynamic temperature, and luminous intensity were added to the system. And in 1971, the mole was added as the unit for chemistry and expressing chemical amount. And this gave us our international system of units as we know it now. And because of the French origins and the dominance of the French language in the system, we often refer to this as the System International, so SI for short. Next slide, please. And this SI system has the 7 base units that you can see down the left-hand side there. These are independent base units, so the kilogram, the meter, the second, the mole, the ampere, the Kelvin, and the candela. And these 7 independent base units give us everything we need to form derived units made from combinations of these to measure anything we can think of. So some of these are very simple derived units like area in meters squared or velocity in meters per second. And some of these are more complex derived units, which we give special names to, such as the Newton force, the Pascal for pressure, the watt for power, which I'm sure you're all aware of. So next slide, please. And these units remain part of this Meter Convention, which really is a worldwide treaty. And as of the end of last month, in August 2022, we had 63 member states of the convention, and 37 associate states. Now, importantly, that covered more than 98% of global GDP. So in economic terms and trade terms, really universal treaty. And the treaty is looked after by national metrology institutes all around the world, just like MPL, maintaining their national standards and comparing those internationally to make sure they're still comparable. So next slide, please. And this SI is a very important measurement system because it has three properties. It's stable, it's comparable, and it's universal. And if a measurement system is stable, it means we can have confidence in trends over time. And this is very important, for instance, in measuring CO2 in the atmosphere as we monitor climate change and global warming. If a measurement system is comparable, it means we can have confidence in differences between locations. And the example here is air quality pollution metrics across Europe. And if a measurement system is universal, this is a very important property, it means we can add together different measurements to add value. So combining measurements in, say, weather forecasting of humidity, temperature, wind speed, and so on, adds value to those individual measurements. And taken all together, this SI system also always tends over time to improve certainty in measurement. So next slide, please. How this system works then in terms of how these national metrology institutes make their primary standards useful, we can see on the left-hand side here, it's something we call a traceability pyramid. And this is a physical traceability pyramid. This is an installation outside the National Physical Laboratory of India. And it's a nice representation because it shows we have our SI units at the top, our primary standards just beneath those, and those are used to calibrate hundreds of secondary standards, which in turn are used to calibrate hundreds of reference standards, and so on and so forth. So the pyramid is a nice analogy for the fact that as we go down the pyramid, the number of measurements we consider increases, and also the measurement uncertainty increases. So every time we do a comparison, we're a little bit less sure about the value that comes out. So as we decrease the pyramid, there are more measurements, but they're less certain. And so it's the job of metrology to oversee these links for end users, but also to minimize the measurement uncertainty for end users. And there are two ways we can do that, given the traceability pyramid. One is improving the primary standards that we have at the top of the chain, and the second is reducing the number of comparisons in the chain. And we will come on shortly to how we have recently improved our primary standards in metrology. So next slide, please. I want to say a little bit first, though, about why we have measurement units that we do and why we have the unit systems that we do. So measurement units taken in isolation are arbitrary and potentially independent from each other. So we've seen that we could use a cubit, a meter, an inch for measuring length. And many of these measures have been around for a very long time. But when we combine these measurement units together into unit systems, they are all of a sudden, they're not arbitrary and independent. They are profoundly linked to the equations of chemistry and physics. And this idea of unit systems did not appear until the 19th century, shortly before the meter convention. And unit systems are based on considering how many independent quantities, so how many base units we should have. So next slide, please. The first unit systems had three base units, and these were based on mass, length, and time, as we've seen from the early days of the meter convention. At the turn of the century, 1900s, electrical current was added to that because it was perceived as something that was physically different. And then in the intermediate time, there was some debate over which quantities should join that independent base quantity list. And at one stage, even angle was considered, but that wasn't taken forward. So eventually we found that in 1971, we ended up with those 7 quantities that you see at the bottom there. So next slide, please. And just a final comment on why we have these 7 base units. Well, it's a trade-off between keeping a clear distinction between independent quantities. So if we have too few independent quantities, we don't really represent properly our perception of reality. and also a desire to remove constants from equations. So if we have too many independent quantities, we have to have annoying dimensioned constants within our equations of physics and chemistry. So really it's a balance between those two competing processes. Now, 4 of those base units are clear from physics and our perception of reality, so mass, length, time, and electric current. 3 of the base units that we use currently are not essential in that respect, but they are very useful additions to the system. So amount of substance, temperature, and luminous intensity. So next slide, please. And we can see over time that the international system of units has always evolved its unit definitions and its realizations to meet user needs for accuracy. And that has often meant improving the way with which we can realize those primary standards. And I won't go through these in detail, but you can see over the years, small tweaks have been made to the system to improve it, and also many smaller changes that aren't listed there. But importantly, as we will come on to, no change until a few years ago was made to the definition of the kilogram. So next slide, please. When we talk about measurement unit evolution then and how measurement units have evolved, we need to agree on what a measurement unit is. Now, a measurement unit is something that is fixed, that we can all agree on globally, and it has no uncertainty. So there are 3 options for this: a physical artifact, a material property, or a constant of nature. So a material artifact, as shown in the first box there, was an example of this was the old international prototype of the kilogram that defined the kilogram. Very convenient, cylinder of metal, but the drawback, so that it's a unique artifact that's susceptible to change, damage, and loss. An improvement on that is using a material property. And the example here is a triple point of water cell that was used for realizing the Kelvin until a few years ago. And the benefits of this is we can do that realization experiment in many locations, but on the downside, the realization depends on the purity of the material, the purity of the water, and generally we can only use one experiment for realization. So the ultimate goal that we all want to get to is realization using a constant of nature, and the C there stands for the speed of light as a constant of nature. And if we realize using a constant of nature, it means we can realize our unit using many experiments, in fact, any experiment where that constant of nature features in the equation. But the downside, as we will see, is that those experiments are very challenging. So if we can have the next slide, please, we can see how an example of this has happened over time. So when we think about how the meter has evolved over time, you'll see on the left-hand side in 1889, when it was defined, the meter was a physical artifact, a meter bar. But over time, that became not accurate enough for the needs of science and technology of the day. And so the definition moved in 1960 to being a material property, and that was a number of wavelengths of the light emitted by a krypton gas lamp. And then eventually, over time, that definition also wasn't suitable for the needs of science and technology of the day. So scientists at the time in 1983 made a very clever decision, which was then to define the meter in terms of the speed of light. And what they said was that the speed of light had this exact numerical value when expressed in meters per second. And then because we knew what a second was, it meant that the meter became the distance traveled by light in exactly that fraction of a second. And so the meter had performed this evolution from a physical artifact to a material property to a constant of nature. And that's what we want to do for all our measurement units. So if we have the next slide, please, we can see that the kilogram caused a problem for this, because the kilogram was previously, at the time of the French Revolution, this very inconvenient artifact, a certain volume of water. And then it became, after the meter convention was signed, this more convenient artifact, a platinum iridium cylinder, but one that was susceptible to change. And if we have the next slide, we can discuss a little bit about how we knew it was changing. So the difficulty is the international prototype of a kilogram, when it defined the kilogram, was always exactly 1 kilogram, whatever its mass. Because it defined the scale, it was always exactly 1 kilogram. So how do we know it's changing? Well, all we can do is compare it against its official copies. And when we do that, on the very few occasions that the international prototype was taken out of its safe, we can see that the change might have been up to around 80 or 90 micrograms per kilogram, so about 80 or 90 parts per billion. And so that level of accuracy sets a goal for us in terms of redefining the kilogram in future. We have to have experiments that can do better than that to make it worthwhile changing to a different way of realizing the kilogram. And if we go to the next slide, until recently, that wasn't possible. But advances in metrology and science and technology over the last 30 years have provided us eventually with a solution. And there were 2 experiments that we used. One was to do with counting the atoms in a perfect, almost perfect silicon sphere. And that gave us a constant known as the Avogadro Constant, which is associated with the mole. And the other experiment was an experiment that balanced electrical and mechanical force in something called a Kibble Balance. And that gave us a value for the Planck constant, which is associated with the kilogram. And in the relationship in the middle there, in the red box, you can see that actually the Avogadro constant and the Planck constant are related together to this complicated looking expression on the right-hand side of the equation. But actually all those terms are known very, very accurately. And so what that means is if we measure the Avogadro constant, we get a value for the Planck constant and vice versa. So we had 2 experiments here, which all of a sudden were of the right accuracy to help us redefine the kilogram, and they were able to self-check each other. So if we have the next slide, please. Just a word on the silicon, the counting atoms experiment. So this used X-ray diffraction to count the number of atoms in a ball of silicon, a sphere of silicon. So by measuring the volume of a unit cell and then weighing the macroscopic mass of the sphere, we could get a value for the Avogadro constant. And if we go to the next slide, please. The Kibble balance was slightly more complicated. So the Kibble balance related to a 2-pan balance where we had a mass on each side. And if we go through the, thank you. So we had a current source on one of the coils, which was around one of the pans of the balance. And if we skip forward a couple more, and another one, please. Lovely. So we had this current carrying coil and a magnet around one of the balances. And if we go forward one more on the animation, when we run a current through that, and if we go forward one more on the animation, that produces an electromagnetic force which balances the balance. And we can write that down in terms of a difference in mass. So we can work out the difference in mass between those 2 mass pieces as a function of the magnetic field strength of the magnet B, the length of that current conducting coil L, the current that's going through it I, and the acceleration due to gravity G. Now it turns out, without going into too much detail, that B and L in that equation are very difficult to determine and can't be determined with enough accuracy to make the experiment work. So if we go forward on the animation and a couple more clicks, please. Oh, that's disappeared from my screen, the presentation. There we are. Great. So we put an instrument called an interferometer at the bottom of the pan, and that allows us to measure the distance and the speed of the pan. If we click through again, the second part of the experiment is to move that pan through the magnetic field. So if we click again, and we register a voltage if it moves at a certain speed. So basically we have a second equation when the balance is falling, and you can see that also has those terms B and L in it. So if we click through again, and in fact we can click through now to the next slide, we can cancel out those terms B and L and get this thing called the Kibble Equation. And the Kibble Equation is a way of defining this mass in terms of things we can measure very accurately. And if we click again, the upshot of this is that we doing this measurement means that we get a very accurate value for the Planck constant, which we can use to redefine the kilogram. So if we go to the next slide, please. The upshot of this was that this revised international system of units came into effect on the 20th of May 2019. We had new definitions for the kilogram and the mole in the ways that I've described using those experiments. The ampere and the Kelvin also changed in similar ways, which I haven't gone into in this presentation. And the definitions of the meter, the second, and the candela were also expressed differently. And this was the result of amazing progress in metrology over the last 30 years or so. So next slide, please. We have now then a system of units where these constants that we use to define our system have these exact numerical values when expressed in those units. So a very different way of thinking about our system from artifacts that we used to use. Next slide, please. So one of the drawbacks potentially of this system is it means we've moved to more complex unit definitions. So for many years, we had a very simple definition of the kilogram. The kilogram is the unit of mass. It's equal to the mass of the international prototype of the kilogram, very simple. So now we have arguably a better definition of the kilogram, but in terms of how we can write it down, it looks more complicated. So it talks about the kilogram is defined by taking a fixed numerical value of the Planck constant. So arguably much more difficult to teach, even though we have now a more accurate realization. So next slide, please. So in summing up then what's happened here, we've had our 7 base units that I've described, and they're all linked together. And before May 2019, we had 3 definitions that were based on fundamental or conventional constants. We had 3 definitions that were based on atomic or material properties, and we had that 1 definition that was based on an artifact, the kilogram. And if we go to the next slide, we can see that after 2019, once these changes have made, and we've based now 6 of our definitions on fundamental constants, we have a much longer list there. They're the same units, they're the same size, very importantly, the size of the kilogram hasn't changed. They have slightly different links because they're based on different ways of realization now. And we just have that 1 unit left, which is based on an atomic property. And I won't go into detail now, but the second is actually very difficult to realize in terms of fundamental constants. So if we go to the next slide, please, and click once. I think previously we can summarize this by saying previously we had unit definitions like our physical artifacts or our material properties, and we use those to measure natural constants. And what's happened in the new SI, if we click on again, is that we've completely reversed that paradigm. So now we have unit definitions in terms of natural constants, and we use those to realize our units. So if we go to the next slide, please, why that's important for the future is because we need a measurement system that is future-proofed for what may happen in the future. And certainly the last 40 years of changes in mobile phone technology have told us that we can expect similar advances in the next 40 years. And we expect things like quantum computing, 5 and 6G communications, smart cities, Internet of Things, all to affect that. And so we need a measurement system that's future-proof. And now we have a measurement system that's based largely on these fundamental defining constants. It means that improvements in technology can be realized directly by more accurate measurements. And that's really important. And it means, if we go on to the next slide, that we have this virtuous circle where improved measurement leads to improved technology, leads back to improved measurement, and that future-proofs our international system of units and means that we can measure absolutely everything we want into the future with an accuracy only dependent on the technology that we can come up with. So next slide, and thank you very much.
Well, that's fascinating. I was just writing some notes here of a number of questions that have come in. And indeed, one question from Richard in Murray has come, and it's about the SI standard system. He says, is the system going to continue to evolve, or do you think there could be yet to come maybe one more step change at some time in the future?
Well, that's a very good question. So we'd certainly never say never. We're certainly not the finished article. One thing which may happen in the next 10 years or so would be a redefinition of the second. So you'll notice from the presentation there that the second is still defined by a material property, which effectively is the oscillation of an atom. Now, it turns out that the clocks we have can now do a lot better than that. They have atoms that oscillate at a much higher frequency and therefore define the second more accurately. So it's very likely that in the next 10 years or so, we'll have a new definition for the second based on a different transition. So that's the one coming up. I think future ones may happen, but it's difficult to foresee at the moment what they would be, but they may well arise.
There's also a question about international collaboration, because we tend to think of international meetings and discussions as sometimes very long, very protracted, with each country naturally wanting to look after its own interests. And sometimes we can wait and wait and not very much comes out of it. Is that the case with international meetings about standards of measurement, that each country has a particular angle, or is it more harmonious?
Again, that's a very good question. So some of these meetings to do with comparisons of standards are fairly well defined. So we've all agreed on what these units are and we compare them. Those are relatively short and they're very productive because the data doesn't lie. Some of the meetings that are maybe a bit more protracted involve when we're trying to discuss definitions for new terms, and they can be a bit more protracted. And as the questioner has said, when we have larger meetings, they can take longer. So I think it's a balance. Certainly the technical discussions tend to be very well controlled and a lot shorter.
And related to that is a question from a listener in Murray about the way in which the meter has gradually dominated over the imperial system. And the questioner says, well, given that Britain was very much a dominant superpower in that period, that the USA was the main superpower since World War II, how did the meter manage to come in so successfully?
Well, very, very good question. So the meter was the original term used in France after the French Revolution, and it spread then quite widely within Europe. So I think by the time that the meter convention was signed in 1875, it was quite clear that it would be almost impossible for countries wanting a different unit of length to get that universally accepted. And that's ultimately what we're talking about. So it's universal acceptance. And I think it was very clear that the meter had to be the universally accepted unit. Now, of course, we will be aware that some countries use different units for certain things, and they're very within their rights to do that. That's a legal issue within that country. So, for example, we still have in the UK our road signs in miles and our speed limits in miles per hour, but those are not independently realised. All those other units are traceable back to the metric system and the meter. That is still the prime system. Even if measurements are expressed in different units, they're converted from the metric equivalent.
There's a two-part question from a listener in Kirkwall, and it's about what might be described as the ultimate challenge. The listener says in the last 10 or so years, there's been two developments in physics that many people would have said were impossible. One being the discovery of the Higgs particle, and the other being the discovery of gravitational waves. Now, in each case, it was a triumph of measurement. The two parts to the question are, first, can you think of any other equivalent, magnificent successes that would be in the history of metrology that would be worth highlighting? And the second one is there something ahead that is equally like climbing Everest?
Well, I think I'll take maybe the second one first. So what's ahead? I mean, it's discoveries like the Higgs particle and gravitational waves that open up possibilities for new ways to define units. So I think in terms of what's ahead, I think those types of things, we may see those feature in the far future, who knows. One of the huge challenges would be to define the second in terms of a fundamental constant. And in order to do that, we would have to measure the gravitational constant, which is another constant of nature, with significantly more accuracy than we do now. So that would be perhaps one of the something ahead major challenges. I mean, in terms of the success, I would point to the story that I've described here as one of those successes. So 20, 30 years ago, the accuracy was nowhere near what was required for the silicon sphere experiment or the Kibble balance. They were probably 2 or 3 orders of magnitude, so 100 or 1,000 times less accurate than what was required. So the advances over just that period of time to make this change have been amazing. So I think really the story here is the success story, and then the future will be using these discoveries in physics to help us find other ways of defining units.
Back in the 1960s, first-year physics students at Edinburgh University had a course by Professor Norman Feather based around his book Mass, Length and Time. And he wanted to bring the importance across to them from the start of the measurements themselves and the history of the measurements. Do you think that this is something that more can be done to help and stimulate interest in physics and interest in physics courses to bring in more information about measurement and its history?
I think it's a very good point, because we certainly, from our point of view, metrology underpins the certainty with which you can do science. It underpins reproducibility in science. And if your science is reproducible, it means you make conclusions faster, you're more efficient, you waste less time. So I think really we would be very keen to see the principles of metrology embedded in as many courses, undergraduate courses, as possible, because I think it gives a really good perspective on why measurement matters for making progress in science.
Richard, you've put it across so well this morning. And just before rounding off by thanking you, I should say that our next talk will be an in-person one. It's the Arctic Whalers with Len Wilson and Dennis Davidson in the Phoenix Cinema, after which at 2 o'clock, there'll be the story of the man who ran the Kathleen Annie. And then we'll be back online at 3:30 with Alec Crawford, Treasure Islands, Stories of Marine Salvage. But in the meantime, I would like to warmly thank Professor Richard Brown for so ably continuing what's now become a great tradition for the Science Festival, this annual contribution from the National Physical Laboratory. So warm thanks to you, Richard, and warm thanks to the technical team for running everything so smoothly behind the scenes. It all remains to me to do is thank you, the viewers and listeners, and good morning for now.